What is going on YouTube? Just helping you out here. And for today's video, I will be doing Chapter 18, Problem 12 in the Fundamentals of Physics 8th edition textbook by Walker, Halliday, and Resnick. Chapter 18 is all about temperature, heat, and the first law of thermodynamics. And in Problem 12, we are asked to compute the increase in surface area of an object that is being heated. And so the first thing that I'm going to do is just draw a picture. And so our cube, which I'm going to draw from just one face, so it's going to look like a square, has a side length of L1. And then after it's heated, it's going to expand a little bit. And so after the expansion, we'll call the side length L2. And so then I'm going to define a new variable, delta L, which is going to be the change in the side length between the heated and the original, and that's going to be equal to L2 minus L1. So essentially, this is just the amount the length of the side increases by expansion. And so we know that the area of this square is L squared, the length squared. So that's just L squared, but we are looking for the surface area increase of the entire cube, and a cube has 6 faces, so it's 6 times L squared. And so what we can do is write the area for both cases of this cube, and that's A1 is equal to 6L1 squared, and A2 is going to be equal to 6L2 squared. And now since we are looking for an increase in surface area, which is the same thing as saying we're looking for a change in area, we can say the change in area is equal to A2 minus A1. And we just found both of those right here, so we can just plug those in. 6L2 squared minus 6L1 squared. And now we're given L1 in the problem, but we don't know what L2 is, so we need to write it in terms of things we do know or things we can solve for. Now over here, I wrote down this little equation, and again, we know L1, and delta L we can find via a linear expansion equation. So we can rearrange this for L2 and plug it into here. So I'm going to add L1 to both sides, and that's going to give me L2 is equal to delta L plus L1. And now I'm going to take that and plug it into here, and so that's going to give me 6 times delta L plus L1, entire quantity squared, minus 6 L1 squared. And now I can expand this out a little bit. That's going to be 6 delta L plus L1, delta L plus L1, minus 6 L1 squared. And now I'm going to multiply these two out. So that's going to be 6 times delta L squared plus 2 L1 delta L plus L1 squared minus 6 L1 squared. And now I'm going to distribute this 6 out, and that's going to be 6 delta L squared plus 12 L1 delta L plus 6 L1 squared minus 6 L1 squared. So these two terms are going to drop out, and we're going to be left with 6 delta L squared plus 12 L1 delta L. And now, as I said before, we know L1, but we are not told what delta L is, but as I said up here, we can solve for it using a linear expansion equation. And so delta L is equal to the length times a coefficient of linear expansion, which is characteristic of the material, times a change in temperature. And so this length is the length that we started with, which is going to be L1. So this is L1 times alpha times our change in temperature, which we'll just say is T2 minus T1. So temperature at this scenario 2 minus temperature 1, our scenario 1. And so now we can take that and plug it back into this equation, meaning that our delta A is equal to 6 times L1 times alpha times T2 minus T1, that entire quantity squared, and that's going to be plus 12 L1 times L1 times alpha times T2 minus T1. And just to simplify it a little more, we have 6 L1 alpha T2 minus T1 squared plus 12 L1 squared alpha T2 minus T1. So we are given all these values in the problem except for alpha, and I said alpha is the coefficient of linear expansion, which is a function of the material. The material that we are given in this problem is brass, and you can find an alpha for brass in one of the tables in the chapter. Okay, so this is equal to 6 times 30 centimeters times alpha, which in that table you would find 19 times 10 to the negative 6th per degree C. That's going to be times 75 degrees C minus 20 degrees C. That entire quantity is squared, and that's going to be plus 12 times 30 centimeters squared times that alpha again, 19 times 10 to the negative 6 per degree C, and then times our temperature difference again, 75 degrees C minus 20 degrees C. And so those two terms are equal to 0.0059 centimeters squared and 11.3 centimeters squared respectively. And if we add those together, our increase in surface area is equal to 11.3 centimeters squared, which if you decide to round it to two significant figures is 11 centimeters squared. And so the reason why I showed both of these terms right here is to show that this term right here was much, much less than this term, to the point where it was insignificant for your final answer, even if you rounded to three significant figures instead of two. And that goes back to up here, where you have this term right here, which delta L I said is the expansion of the length of a side of the cube due to heating, which is pretty small compared to the length of the cube. So this term could have been discarded, and you just would have been left with this term, and had you done the math, which would have been less than what I showed here because you wouldn't have had that term, you would have been left with just 11.3, which ended up being our final answer if you rounded to three significant figures. So basically I just wanted to point out that was a simplification that you could have made to make your life a little easier, because in this particular case, that term would not have mattered. And so this is the final answer to this problem. And so that's about it for this problem. If you found this video helpful, please drop a like, leave a comment if you have any questions or an idea for a future video, and lastly, please don't forget to subscribe and tell your friends about my channel so I can grow and help more of you guys out. I'm just helping you out. See you in the next video.